Okay, the projector is apparently broken today, so we're gonna have to do this old school, I guess. We'll figure it out. A couple of announcements before we begin today. Of course, we have an exam 1 week from today, so we will have a review session next Tuesday. I'll plan a set of review questions. Please bring questions of your own on Tuesday. If last time is any indication, we will definitely not have time to get through all the review questions. So please bring some ideas of what areas you would like to concentrate on so that I can make sure to focus on those. I will post answers to the review questions just like I did last time. Homework 3 is in the process of being graded, and I really hope to have that back to you by Tuesday. I cannot make that guarantee at this moment in time. But I do have the answer key for homework 3, and I will be able to post that later on tonight, actually. I had a few people who used their late coupon on homework 3, so I couldn't post it, but that deadline is passed. So I will, at the very least, post the answer key to homework 3, so you can use that to study, and hopefully get that back to you on Tuesday. I do have your Lab 2 grades today, so your Lab 2 grades should be in Blackboard already, so you can check them on there. I will pass those back at a later point. What else? Chapter 4 of the Zybook is due. I think it's marked on the calendar for Tuesday, but let's go ahead and make that Thursday for Chapter 4. Have it done by the exam date. I think that's about it. Yeah. Are there any questions about exam stuff or other logistical stuff before we try and do some practice problems? Okay. So I don't have this projector. I might try to fix it again later, but we'll just have to do the best we can with the resources that we have. Actually, I am streaming this on YouTube, so if you have your laptop, you could pull up the stream on YouTube and use that. Or the slides are on the course website, so you can pull up the slides on the course website and follow along with that. That might be the best thing to do. In the meantime, so the first question deals with multi-bit multiplexers. So we've actually been using those, right? We've actually already been using those kinds of multiplexers. So here's an example that was used, I believe, in the video, something like this, where I'm not just choosing from one bit or the other. I'm choosing from this set of 3 bits versus this set of 3 bits. Right? So all of my inputs are 3 bits, all of my outputs are 3 bits. So my first set of questions for you are how many lookup tables, right, is it going to take to implement certain sets of muxes? We talked about this a little bit ago, so this is a good review for the exam, right? So here's 2. I'll draw 2 more muxes on the board for you to figure out as well. And we also, I think, when we talked about lookup tables, talked about a formula that you could use to determine how many lookup tables are necessary. And I promised you that we talked about that, and then I didn't. But I would like to wrap that up today. So see if you can figure out what that formula is. How many lookup tables do I need? If I look at a given circuit or a given component, you should be able to tell how many lookup tables you need. See if you can figure out what that equation might look like. And we will go over this in just a few minutes. Whoops, that's not what I wanted. And then finally, and for this we're using 4. Kind of winging it. Marker is off. Suppose I could turn the lights on so I'm not using Oh, that works. And just power cycle, which takes a long time. So after that's over, yeah, maybe it doesn't work. So how many lookup tables do I need for this guy? Anybody figured out? How many lookup tables do I need for this one? Get a table. Make that happen. Yeah. Just 2. Okay. So we've got, we're using 4 input lookup tables, right? So 1, 2, 3, 4. Lookup table 1, 2, 3, 4. And how do I wire these together to make that a duplexer? You have the first 3-bit input. And select bit. Oh yeah, I forgot the select bit, didn't I? All right, so I've got the first 3-bit input, right? So these 3, let's say, in the select bit, and then you have the output of that go into the next lookup table, also within the 3-bit input, the other 3-bit input, and then okay. So yeah, that's kind of the snag here, right? Is that this is going to give me only 1 bit out. Yeah. So in theory, it looks like it should work, but unfortunately, I can't quite swing it. I know I need at least 3, right? 3 is minimum. 3 is bare minimum. Can I do it with 3? Do it just 3? People shaking their heads, no. Why not? Why can't I do it with just 3? So what's inside of this mux, right? What's inside of here? We've actually got 3 of these. We've got 3 of these, right? They're all coming out, right? So this is, or I'm sorry, they would be, yeah, no, that's right. We've got 3 2 by 1 muxes in there. That's what's actually inside of this guy, right? So the question is, can I implement this with a single lookup table? Yes or no? Yes. Yes, I can. Yes. So three 4-input lookup tables will work here. Each of the lookup tables will have, 2 input bits and a select bit, and then they'll have that 1 output bit. So 3 is the correct answer for this guy. 3. Yes.
What's the proper way to deal with that the extra inputs? Can you just wire up?
You just leave them. Yeah, you could just. They're not used, so you could tie them to ground or something that doesn't matter. Or, yeah. Just leave them hanging. Yep. Okay. So what about this one? We've got a 2 by 1 box with 4 bits going in, 4 bits coming out. How many am I going to use that one? I mean, that's just one more mux, right? That's just one more 2 by 1 mux. So I should be able to do it in 4. Okay. All right, well, let's take a look at these then. So now I've got a 4 by 1 mux with 2 bits going in. So let's think about what's actually happening here. What do I have on the inside of this mux? I've got 2 4-input muxes. Right? So how many lookup tables do I need for a 4-input mux? You need at least 2, right? Because I've got 5 inputs. I can't take care of all 5 of those inputs with just 1 lookup table. I'm going to need at least 2. 2 should cover it, though. Since I got 2 of these, then that should give me 4 lookup tables total for this guy. And then this just adds another 4 by 1 mux, right? So this should be 6 lookup tables total for that one. Is anybody able to formalize, put this into a formula that we can use to help us determine the lookup tables? Yeah.
The number of lookup tables for the mux ignoring all of the inputs times the number of bits.
Ignoring all, let's do that one more time, times the,
Like you essentially just get rid of the number of bits that it's dealing with, and then you come up with the number of lookup tables for that based on our old lookup table formula, and then multiply it by the number of bits.
yeah, so I was thinking of a general that would encompass not just multiplexers, but every circuit that we saw. The equation that we saw last time, I think, only dealt specifically with single output circuits. These are multiple output circuits, so I think that's the wrinkle in deriving the formula here. What if I'm not talking about a mux here? What if I'm just talking about a circuit in general? How many lookup tables is it going to take me if I have X number of inputs and Y number of outputs? So it's a function of the inputs and the outputs. What it ends up being is the number of inputs minus the number of outputs over 3, and then take the ceiling of that. Get you the number of lookup tables. The number of 4 input lookup tables, right? Where does this 3 come from? Where's that magical 3 come from? Yeah. 4 minus 1, so feeding the output of a lookup table into another lookup table, right, gets us the 3. So if I use a 6-input lookup table, right, this becomes a 5. Right, so you can modify this expression for whatever size lookup tables you happen to have handy. There's still potentially an issue with this. What am I assuming? This equation about my circuits. If there's more inputs than outputs, if I have more outputs than inputs, then this goes negative, and that's not necessarily what we want, right? So if I have more outputs than inputs, how does that work then? How many lookup tables do I need if I have more outputs than inputs? I just need as many as I have outputs, because they've got 1 output per lookup table, and the lookup table should have enough inputs to cover, it. That may not always be true. You would need at bare minimum as many lookup tables as outputs. That's trying to think of a counterexample where you would actually need more than that. Not sure if I can come up with one off the top of my head.
Crazy circuit where you had 15 inputs and 20 outputs, but
Yeah.
each output depended on all 15 inputs.
Yeah, then you're running into problems because you would need to. Each output depends on all 15 inputs. That would require a lot of lookup tables. Yeah, that's not a math equation that I want to do in my head. I have to sit down and write that out. But this works assuming that I is greater than O. This works assuming that I is greater than O. And actually, more often than not, this is going to be true. We have seen cases where this is not true. Anybody think of a case where I is less than O that we've seen before? What kind of a component? A decoder, right? A decoder has more outputs than inputs. You've got 2 things coming in and 4 things coming out, for example, in a decoder. So that would not work for this. How many lookup tables would I need for such a? 4 should do it. Right? There's only 2 inputs. But if I get up to larger decoders, that becomes a harder question to answer. Okay. This will work. This will work the vast majority of the time. Are there any questions? Questions? Yeah. So yeah, sure. What is a lookup table? Can somebody tell me what a lookup table is? What do I mean by a lookup table? How does a lookup table work? Nobody? Oh, I should ask about this on the exam then. Yeah.
It computes all the outputs of your circuit based on the inputs, and essentially just the same code.
Yeah. So we are trying to implement a circuit, right? But we don't necessarily we want our hardware to be flexible. We want our FPGA to be able to implement whatever circuit we throw at it, not just particular kinds of circuits, but any circuit. So instead of having just a whole bunch of gates lying around that we hook up in various ways, however that might work for our different circuits, you could conceivably, right, do it this way if you really wanted to. Just have a whole bunch of gates sitting there and then hook them all up in various ways to create the circuits that you want. Instead, what happens is we design our circuits in CAD tools on Xilinx, right? And then it goes through and it computes what all of the outputs are for every single set of inputs. So I have 4 inputs here. How many possible combinations is that? 4 different binary inputs is how many possible combos? 2 to the 4, which is just 16, right? So this lookup table has 16 possible outcomes. It's just going to pre-compute all 16 of those and hard code them in. So that when you actually run this on the FPGA, when you put your code on the FPGA, it doesn't actually run it through the circuit. It's just doing a whole bunch of lookups from a table, based on what the inputs are. It's actually a lot faster as well to look something up from a table instead of processing it through all the different gates. Yeah. Well, that's what I was asking. I'm saying if I'm creating a circuit in VHDL or something else that uses a Mux, how many lookup tables is that going to use on an FPGA? It's a question that's important to ask because we're limited in terms of how many of these lookup tables that we have. So we need to implement the Mux. Yes, that's what the questions are asking. Yeah. And so there is not an infinite number of these things, so it's good to know, will my circuit actually fit on this FPGA or not? Yes or no? Right? Did you have a question?
Yeah, could you go over specifically the last one? Let's say 6 lookup tables?
Sure.
The formula does not get the right answer.
The formula does not get the right answer for that. Interesting. Okay, well, let's take a look. So we've got this guy here. We can do that in 2. So we need 2 Muxes for this at least because we've got 4 inputs plus the select, so that's 5 inputs. We can't cram that into one lookup table, so we need at least 2 plus the 2. Oh yeah, there's 2 select bits. Thank you for a 4. I've been drawing this wrong. Thank you. 2 select bits. So we need at least 2 for this, right? So with that logic So what we said was that would be 3 of these total, so that should be 6 lookup tables altogether. And so if we crunch that through the formula, what happens? We get 12, 14 inputs, right? And 3 outputs, so 12 minus 3 is 9, divided by 3 is 18 inputs, yes. 6 per mux, and there's 3 mux.
Oh, wait, no, never mind. Never mind.
The selects are the same.
Yeah, they're the same property, but then the formula is
Yes. Hang on a second. Hang on a second here. Well, so the way that we constructed this, you were actually correct to assume that each of these have 2 select bits because we are using both select bits for every single mux that we have, right? So that is the correct assumption to make in this particular case. So that would be that would actually be 3, 6, 9, 12, and then 4 or 3 of these, so that would be 18, like you said. So that would be 18 minus 3, which is 15, over 3, which is 5. We're off by 1. How did that happen? Let me think about that for a second.
And there might be a way to do it in 5.
There might be.
You just don't logically.
Right. There very well could be a way to do it in 5. I mean, you have to consider that we kind of did this in a simplified way by using muxes to represent this. There's actually logic gates inside of here that are being represented that way, so that actually changes things a little bit in terms of representation of the lookup table. It's possible to potentially try to, well, is it though? I'm trying to think of how you get rid of the lookup table. The math makes sense. I mean, if you have 5 lookup tables, that's enough to cover 18 inputs as well as 3 outputs. So the math makes sense for that.
Currently in our 6 lookup table, every other lookup table is not utilizing 1 input.
Right. So we're being a little inefficient in that regard. So the formula suggests that there's a better way. But it's a good question. I mean, how can we actually write it such to use only 5 instead of 6? I mean, let's just try and write it out, I guess. See if we can determine a logical way to make this happen. So we could use right. So that can be I guess I'll call this A for that signal coming in. But then we need select bits coming out. I think actually, what if you did, so you could then say B. I think this might be it. Hang on. A and then B. No, that wouldn't work. Nope, I would be too clever. If you're using 5, you would need at least 3 for each of the outputs. That means you could only have 2 extras, like two lookup tables feeding into 3 somehow. That doesn't work in this case. So something is a little off. I'm just trying to figure out what. Five. I am drawing a blank. I mean, it's a good question. I'm going to figure it out. This is going to drive me crazy. But I think for the sake of time, I'm going to move on right now. However, what I am going to do is make a note to take a look at this later so that I can get you a proper answer, and I will post that on Piazza, or if I don't post it on Piazza by next Tuesday, somebody should hold my feet to the fire and ask this question again next Tuesday. Please do. Okay. I know that's not satisfying, but I need to take some time to figure this one out, and I don't want to do that right now. So, thank you for bringing that up. Let's try a different question.
Could you still go over the 6, for example, though?
Sorry?
Could you just go over how the 6 input,
The 6? Well, sure, yeah. So for each of these, right, I've got 4 inputs coming in, and then 2 select bits coming into this one. So these are my selects. and then this is the output for that particular bit, right? And so then I would have, well, wait a second, 1, 2, 3. I've got 3 4-input muxes. Yeah, so these are this is 4 inputs from one mux. These are the 2 select bits for this mux, and then this is the output of that mux. And then I just multiply this.
Oh, the other 3.
Yeah. It'd be the same structure 3 times in parallel. Remember? That was how we came up with the 6 solution. There very well could be a way to do it in 5. I just need to sit down and try to figure it out before I give that answer. Cool. All right. Any other questions? All right. The second set, which I know you still can't see on the screen, but hopefully you have in front of you, asks you to determine what the different timing configurations are for a load register. So what's the difference between a load register and a regular register? We've been using so far? Yeah.
Load register takes the load signal that sets. It only changes values when the time load is low. It just gets the full value right back into the input.
Right. Yep. So the registers that we've been using up until this point are going to be loaded every single clock cycle, right? We may not always want to do that. Maybe we want to have more control over when it's being loaded. We just don't want to automatically load the register every cycle. So we can add a signal that allows us to choose when this register is loaded. And so my question for you then is, if we use a load register, how's that going to affect the hold time, setup time, and the propagation delay of that particular register? Take a few minutes. We're assuming 2.5 seconds of delay for our gates, which is kind of our standard assumption for delay. Take a few minutes, see if you can figure out what those timing constraints would be for a load register, and we'll talk about the answer in a few minutes. Yes. So we're taking the total number of inputs and subtracting the outputs from it. Um, I suppose it is possible that I wrote down subtract instead of plus.
Intuitively, why do you need one lookup table if you have
18 inputs and 17 outputs. You're right, yeah. I think it should be plus instead of minus. Is that the solution? That could very well be the solution.
Yeah, because that would also give you 6 instead of 5.
Yep. You're probably right.
Yeah,
5 plus Does that work for the other examples too? So we have 6, 7, minus 7, 3, that'd be 10. Divided by 3 is, I'd say 4 for that one, but we can clearly do it in 3.
yeah. Okay, so maybe that's not it either. I don't think that that's it either. Just trying to
No, it's
question the formula.
no, it's a good question. It's a good question.
I mean, is it not maybe it's a ratio of inputs and outputs that you have on there? Because I think this might be a bit complicated.
I think it's actually a lower bound is what it is.
Okay.
So we're not saying that's exactly how many you need, but it's lower.
Okay, so that is less than or equal to the number of lookup tables, not
Right. Yeah.
strictly. Okay.
Yeah, and that's an important implication, right?
Yeah,
So
that is, that's very important.
yes. Um, yeah. The number of lookup tables has to be that or greater. Sorry. Yeah. And that solves all the problems.
Yeah, and then the other lower bound of the lookup table must be greater than or equal to 18.
Right. I think that's it actually.
Yeah, so if we lower bound it in those 2 ways, then we can start to do things.
Sorry. Wrong way. Right?
Because I can't logically come up with a way that you
Yeah.
ever be able to do it with 5.
I can't either. I've been thinking about it ever since you asked me.
Yeah.
I think you're right.
Because you have one lookup table that's all by itself, and there's no way.
Yeah, there's no way to do that. Nope.
With a lookup table all by itself.
Nope. I believe you are absolutely 100% correct. So the other one we would then say is LEDs must be greater than or equal to. Yep. Thanks, man.
Yeah.
Much appreciated.
I like formula things like this.
I will be able to get this thing tonight.
Yeah. This is the exact type of problem that it goes through your head trying to come up with it while you're trying to skip. It's also the time when you figure it out and you're just like, oh crap, I have to write this down. So I'm not going to remember this.
Okay, I do want to talk about this problem. Before we talk about this problem, thanks to Eric, right? Thanks to Eric, I believe we sorted the problem with the lookup tables. This was not intended to be an equality, but more bound on the number of lookup tables. So this value has to be less than or equal to, or it might actually be better to say the number of lookup tables I need is greater than or equal to this value, which solves all of our problems. That makes life a lot easier. I do not think there is a way to do this using only 5 lookup tables. I don't think it's possible. Please feel free to prove me wrong, but I don't think you do it. So expressing this as a bound instead of an equality makes a lot more sense to me. And then this is also another bound that needs to be intact for this equation as well. So cool, that's all sorted. Any questions about that before we talk about the next problem? All right, so let's talk about this load register. What then will be the setup time for such a register? We figured out? Yeah. 6 nanoseconds. So let's think about that. We need to determine how many gates. How do we determine the setup time? Actually, that's a good first question. What dictates the setup time? I'm looking at a circuit diagram of a register, or even just a flip-flop. Right? Just a single flip-flop. How do I determine what the setup time is? Yeah. Get to the register. I'm sorry? Get to the flip-flop in the register. Getting closer. What is the setup time again? How do we define setup time? Setup time is, yeah.
It's the time the signal must be held constant before the rising edge of the clock.
How long we have to hold this signal constant before the rising edge of the clock? And why do we need to hold it constant before the rising edge of the clock is really kind of the meat of this question, right? What is the problem with changing it very close to the rising edge of the clock? What problems is that going to cause? So yeah, it could cause metastability. So why? That's really, we're getting closer. We're kind of surrounding the right answer. We haven't quite hit the answer that I'm looking for. It might actually be better if we sketch, flip-flop up here, right? Just going to be these cross-coupled NAND gates. Oops, except I didn't draw them correctly. Right? It's just going to be cross-coupled NAND gates attached to another set of NAND gates. Right? And then there's an inverter as well. It's off the screen. We don't even really need. So it's clock. And then data. I will move the screen in just a second because I know it's in the way. We're not using it anyway, so might as well get it out of my way. Right. So this is a D flip-flop, right? This is a D flip-flop. I'm sorry, this is not a D. Hang on a second, think about this. This is a D latch. A D flip-flop is 2 of these, right? 2 of these put together. So if I imagine 2 of these sketched out, right? One after the other. So here's the next NAND gate for my second side. There's the other NAND gate down here. Right? The clock has to feed in. I think it's actually the inverse clock that feeds into this guy. So what then is the cause of my setup time in this circuit? Where does the setup time come from? It's based on what we're looking at up here, right? Yeah. It comes from this first latch right here. So setup time, the definition of setup time is how long does it take for this signal to get from the input here, part B, to the output. That's the definition of setup time, right? That is what causes causes setup time. Think about what if the signal's traveling through and it gets, maybe this far, and then that rising clock edge comes. What's going to happen? Well, it becomes a race between the clock and this signal. What's going to make it first, right? If this doesn't make it through here and stabilize before the clock makes it over here and switches this D latch, then I'm not going to record the proper value. I'm not going to store the proper value in this register. So setup time is how long does it take for something to propagate through this first flash. So how long does that take? What's the maximum possible time it can take for something to propagate through that flash? If we assume 2 nanoseconds per gate. Circuit. I feel like there's something off about this circuit. I can't quite put my finger on it. Might be right. I don't feel like it is. No, it's fine. What's the maximum path then for the data to take through the circuit? Does it really matter? Just 2 gates. There's just 2 gates in the way either way, right? So it would just be 4. Just be 4 nanoseconds. Regardless of which path you take, you can only take 4 nanoseconds. Or can it? So we have this cross-coupled action.
Yeah.
It could take 6, right? It could take 6 if we have to go through this one, and then loop back around through this one. But you would, well, then you have to ask, well, what if that affects this one as well? How many times do we have to travel through this loop before it stabilizes? We kind of hit an inception kind of thing going on, right? I think you could argue that, let's say this one changes, which makes this one change, outputs that, which makes this one change, outputs that. If it keeps changing forever, what's that called? That's metastability. So we know it's going to stabilize eventually, right? So I think at most we can say this one changes, this one changes, this one changes, and then this one can't change again after that. Otherwise, we're in a metastable state, right? So we've got 1, 2, 3. That's 6 nanoseconds, I think, for that becomes stable, right? 6 nanoseconds. So our setup time would be 6, right? No, why not?
Because you have your
We've got our mux. Get that mux in the way. So how does that affect our setup time? 4 more nanoseconds. There's 3 gates in a 2-input mux, but I only have to go through 2 of them. Yeah. Oh, there is an inverter on one of the inputs, so that would be 3 gates. That so it would go through the inverter, the AND gate, and the output. Right? For the longest path. Is there a question in the back? Well, this is a latch. I started drawing the second one over here, but for setup time, this latch doesn't matter. It's only the first latch that matters for setup time. The second latch here does not matter for setup time at all. Doesn't make a difference. Yep. Okay, so we decided then that, let's see, we've got 3 gates here plus 3 gates in the box, right, for 12 nanoseconds total for setup time. Any other comments, questions on that? So that mux kind of mucks things up, right? Oh, that was bad. Sorry. Sorry. Sorry, not sorry. What about hold time? How do we determine hold time? What causes hold time? Setup time is caused by the data traveling through this latch, right? What causes hold time? What is hold time? How do we define hold time? Yeah. Right, so setup is before the rising edge, has to be stable. Hold time is after the rising edge, has to be stable. So what causes that after the rising edge? What's making us wait? Getting in the way. What do we want to happen at the rising edge of the clock? What's happening when that rising edge of the clock hits? I've got 2 latches here, right? So before the rising edge of the clock, what's this latch doing? It's reading in information, right? It's taking in information. Whatever D is, before the rising edge of the clock, this latch is sitting here waiting. It's actually hang on, I need to say this right. It's actually going to be storing this particular value, right? This inverter is in the wrong place. This has been driving me crazy, sorry. It's been driving me nuts. I think this goes over here, and then the inverter is like down here. After it. Sorry. Anyway, is that right? That's not right. I had it right the first time. Sorry.
You want the first one to be an enablement.
I know.
Before the right.
Yeah. I'm just doubting myself. I shouldn't do that. Okay. So before the rising edge of the clock, let's get back to what I was. Get back on track here. Before the rising edge of the clock, right? This latch is going to be accepting data or no? Yes, it's going to be accepting input, right? It's going to be accepting data in. And as soon as that rising edge of the clock happens, this is going to turn into storage mode. It's going to be stable, right? It's going to wait. This latch is doing the opposite. Before the rising edge of the clock, it's holding stable, and after the rising edge of the clock, it's going to read in whatever that value is. So that's how this flip-flop works. Which part of that cycle matters as it in respect to full time? Which of those four different scenarios that we have? Yes.
Use the inverter story.
Yeah, I thought it might be. It's been bothering me here.
Yeah, that's definitely not where it goes, because like there shouldn't be an inverter on the wire carrying the clock. The inverter is part of
The clock is inverted before it gets fed into this latch.
yeah.
Right? That's what I was trying to illustrate here. I think this was right. The clock is fine this way, but it gets inverted before it comes in here. Right?
No. But like the inverter happens, the clock doesn't get inverted before it gets fed into the second latch. It gets inverted before it gets fed into the first latch. But the way that you had it drawn previously, you inverted the clock for both latches.
I'm getting confused now, so I'm just gonna Google it.
Yeah. Like there's more than one inverter.
Okay. Got it. There it is, right there. That's what I'm looking for. I almost had it. I almost had it. So we've got D actually needs to be inverted as well. I forgot that. And then the clock, as far as the clock goes, we get this. Yep. That's what the Google is telling me.
Yeah.
This is what the Google says. So here's clock over here. There you go.
You can get rid of one of those inverters.
Probably so.
Yeah.
Probably so.
Like if you put one inverter on the wire going up instead of two.
I've got clock coming in two different places.
Where you have your little T junction between the two inverters.
Okay. Yeah.
You put the inverter there instead of two inverters on the wire.
Okay. So we still haven't answered my question of what causes hold time delay. What causes our hold time constraint? Where does hold time come from? Why is hold time a thing? Can we get somebody else chime in here? Maybe somebody in the back who's staring at their phone? Nobody? I'll wait. I got time. You guys got time? Somebody could have looked it up by now. Seriously? Anyone wants to tell me what's going to cause hold time? Cool. I know we talked about this. Yeah. It's not the second latch in the flip-flop, actually. What causes hold time? So what's important at the rising end of the clock? These flip-flops are changing the states that they're in, right? This one goes from reading to storing. This one goes from storing to reading. How does that change happen? How does this change from reading to storing? How does this change from storing to reading? What makes that change happen? Yeah. The clock. The clock is what makes that happen. But the clock needs time to propagate through the circuit. The change in clock needs time to propagate through that circuit. So that is what causes hold time. The clock signal needs time to actually change the states of these flip-flops. Right? That's what causes hold time. Please, please, please go back and review that information. I know we covered that 2 or 3 lectures ago whenever we did the timing section. Hold time is caused by clock propagating through this first latch specifically. The second latch is not actually as relevant to the hold time. It's primarily the first latch. So with that in mind, what is the hold time? How long is it going to take, right? I got to get through this inverter. I got to get through the same number of gates as last time, right? So it should be 8, I think. 1, 2, 3, 4, 8. 8 nanoseconds for hold time. The mux doesn't matter. The mux is out the window here. The mux is not connected to the clock at all, so we don't have to worry about that. This first latch here. So we had 12 seconds for setup time, 8 seconds for hold time. What was the last one? Propagation delay. So what causes propagation delay? It's the one thing that we haven't blamed for any delay yet. So setup time was based on propagation through this latch. Hold time we blamed on the clock. What haven't we blamed for any delay yet? Yeah. Second D-latch is propagation delay. Second D-latch is propagation delay. Right? So propagation delay is going to be based again on this latch configuration. How long is it going to take our data to progress through the latch? We actually kind of already did that, right? 1, 2, 3. It take well, so we have to, with propagation delay, we actually express that as a minimum and a maximum. So what's the minimum propagation delay? What's the maximum propagation delay? So minimum, we've got 1, 2, 3. Maximum, we've got this converter in there that we need to take into account as well. So it'd be 6 to 8 nanoseconds in this particular case for the output to propagate from this latch through this next latch. Are there any questions about that? Yeah.
It's minimum 4.
Minimum 4.
Because in theory, you could just go through the 2 and 8.
Oh, yeah. In theory, you could just go through the 2 NAND gates, especially if this one doesn't need to change for whatever reason. Yeah. Yep, good call. Thank you. Minimum is 4. Maximum is still 8, right? Yeah. Maximum is still 8. Please, 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 please review this stuff. Please. We will review it again on Tuesday, of course, but this will be on the exam. I will expect you to know everything we just talked about. Are there any questions? How does this compare with the registers that we've been using, the non-load registers, right? Are those setup hold times, propagation times better, worse, the same? Setup time is faster for the non-load. What about hold time and propagation delay? They don't really change, right? It's not effective. So the load signal is only affected by that mux. So that's all we need to take into account. So the setup time is the only thing that's going to be affected. Okay. Cool. Question number, whoops, wrong screen. Question number 3, the next slide, has you construct a load register that uses T flip-flop instead of D flip-flop. So this is a D flip-flop that we've been sketching up here. You don't need to draw a T flip-flop with the gates, although that is something that I could ask you to do on an exam. Just use the component symbol, right? Here's the T flip-flop. So next question question says, sketch a load register that uses T flip-flops instead of D flip-flops. This one might be a little bit tricky. Maybe start with the D flip-flop version and think about how you would modify it to suit your needs. If you get 1 bit, you should be able to get the other 2 bits pretty easily. So take a few minutes, talk to your neighbors, and we will go over this example in just a little bit.
You know it's following you. Because I didn't really say anything.
I don't know. I didn't know. It looked like you made a typo, but I don't know. Maybe that means that.
Yeah. Like when I was reviewing, I mentioned how it worked. I thought that the B parentheses X meant B as a function instead of B times X.
That's probably
Yeah, because that's totally what it looks like. Who writes that? Who writes B of X and means B times X?
Yeah.
Instead of just BX. Yeah, and then I thought that he had just evaluated B of X.
Yeah. Yeah, that's what I was thinking.
Yeah, because I couldn't, like, after he told us, you're wrong, I'm sure it's 1, I sat there for like 10 minutes trying to figure out how on earth you get 1 out of the equation that I had written down.
Yeah.
Like I couldn't even like do math wrong and get 1. With
Yeah. Right.
Oh,
Yeah. There was like, he had written, yeah, he had written something like, something like one insect for, like, for 2, and then X minus 1 for something else. And then I was like, ah, you have to get a typo. I thought I got it right.
Okay, let's talk about this problem real quick. We got a little time left. So how does a toggle flip-flop work? What does it do? Yeah. If t is high, it flips. What if t is not high? What does it do then? It stays the same. So that behavior actually seems kind of nice, right? If I want it to stay the same, then I just keep this value low. So that might make our life a little bit easier when constructing this register. So what's our approach here? How do I figure this out? How do I decide? What do I need to add to this flip-flop to make it act as a load register? Load flip-flop. Anybody come up with any ideas? So I've got two choices, right? I need to either load or not load. So I think I still need a mux here. The question is, what is the behavior on loading versus not load? So here is load, right? If load is low, I just want to hold the same value. So what value do I feed through the mux then? If I just want to hold the same value, what do I feed through the mux? 0. Let's say don't toggle. Stay the same. Stop. Right? Don't do anything. The trickier part is this. If I tell it I want to load a value in, right, then I need to figure out how to actually record an incoming value. The problem is, what are my possible options? This could be a 0, and I want to read in a 1, which means I want it to toggle, right? Or if this is a 0 and I want to read in a 0, then I need to tell it not to toggle. I need to tell it to just stay where it is. Can you think of how I can accomplish that? Yeah.
Do exclusive or T and Q together.
Exclusive OR. So here's my exclusive OR, right? D, that's my data coming in. Q is the output of the flip-flop. So I can feed that back around into the exclusive OR. And let me label this. So what is this going to look like, right? If the flip-flop is holding a 1 and D is coming in as a 1, exclusive OR 1 is 0, which means it's just going to stay the same, right? If T is storing a 0 and D is coming in as a 1 exclusive OR 0 is a 1, which means it's going to toggle. Right? So it should actually perform the correct behavior. Yeah, this should accomplish it for 1 bit. Just multiply this times 3 and you get 3 bits. Question? Do it with 2 AND gates. Let me draw this so that I can see it. And Q was low with data. And in Q not in your data, what was the other one? And that would load. Like this, and then feed that into T. Is that right? So if T is storing low, this is high. If I want to store low, then this is off. So that will be off. So that will tell it to not toggle. So that's correct, actually. If Q is storing high and I want it to remain high, this would be off. Off. So what's the case if they're different? If T is storing high and I want it to store low, this would be low. This would be low. This would be off. This would be off. Yeah, if they're both, if this is storing a 1 and I want the data to change from 1 to 0, then this would be 0 and 0. So this is off, which means this is also 0, which is going to tell it to remain at 1. It works for 3 of 4 cases.
Well, you have essentially half of an exclusive OR gate from there.
Yeah.
If you do Q D naught and it together and roll that with your Q naught D, that's the definition of exclusive.
Gotcha. Yeah.
And then
This worked for some of the cases, but not all of them.
because your time
Yep.
is 0.
Cool. I think this is the simplest way I can think of to do it. There are certainly probably other ways to go about it, but I think this is the way that I can come up with. The other question on this slide asks you to construct a VHDL module for a 3-bit register. So what would that module look like? What would I expect to see inside that VHDL module? Is this a synchronous or asynchronous circuit? Synchronous or a combination of these circuits? It doesn't have to be a T flip-flop. You can even use the D flip-flop version, right? It doesn't matter to me. Actually, in VHDL, it'd be hard to specify one or the other. You can do it maybe. What am I going to see inside of this VHDL module to implement this register? What do I need? Come on, guys. Process. Might as well get out of here. Nobody's going to participate. See you guys later. Bye. I'm done. See ya. See you on Tuesday. I'm serious. See you guys. Have fun at Wild. If you want your lab, you can come pick it up.